All right, let's dive right into this explainer. Today, we're looking at something absolutely wild, a truly fascinating intersection of extreme biology and bleeding-edge aviation. We're talking about a highly detailed synthetic mission report straight out of the DBbun version 1.2 simulator. And the goal here? To solve literally one of the most punishing engineering bottlenecks in modern aerospace, the DARPA Lift challenge. You know, this really isn't your standard drone engineering report. This simulator takes the raw, natural capabilities of apex predators and migratory birds, translates them into hard math, and then just drops them into a brutal virtual competition.
Now, to really grasp the scale of this challenge, we've got to start with the constraints. 55. That is the strict empty mass limit in pounds for the aircraft. 55 pounds. I mean, in the world of heavy lift vertical flight, that is practically nothing. Think about it for a second. A standard high-capacity lithium polymer battery pack alone can eat up a massive chunk of that allowance. So you've barely got any room left for your high-torque motors, let alone a whole structural frame, the wiring harnesses, or the avionics. Every single ounce is heavily contested real estate here.
But here's where it gets crazy. The real constraint is what that tiny 55-pound drone is actually expected to carry. 220 pounds. Yeah, DARPA is demanding an insane 4-to-1 payload-to-weight ratio. Just try to picture the sheer physics of that for a minute. A machine lifting 4 times its own empty weight, carrying a load that's literally heavier than most adult humans, and then actively flying a demanding 5-nautical-mile competition circuit. It completely breaks standard battery discharge rates, not to mention throwing conventional structural paradigms completely out the window.
So what exactly is pushing engineers to the absolute brink to solve this practically impossible physics problem? Well, how about a staggering $6.5 million total prize pool? That's what's waiting for the ultimate heavy lift VTOL drone at the competition out in Dayton, Ohio. DARPA is essentially laying down the gauntlet here. They're saying, hey, if you can crack this legendary 4-to-1 ratio, the massive payout is all yours. But the big question is, how on earth do you build an aircraft that light, that incredibly strong, and that powerfully explosive off the line?
Well, this is exactly where the DBbun simulator introduces a pretty brilliant evolutionary shortcut. See, conventional military drone tech largely relies on things like rigid carbon fiber structures and your basic fixed rotors. And, you know, it works, but it's fundamentally heavy and kind of brittle. So instead of just slapping on more dense batteries to solve the power problem, which is what everyone usually does, the simulator explores extreme bio-inspired engineering. We are talking about morphing membrane wings that actively adapt to wind camber in real time. We're talking compliant, flexible spines that literally absorb intense aerodynamic shocks instead of just shattering under the immense pressure. It's a total game changer.
So that brings us to our first main area, nature's blueprints, from the zoo straight into the simulator.
Let's explore exactly where these ideas are coming from. The core philosophy of the DBbun simulator is super interesting. It basically uses 9 specific animals as its ultimate R&D lab for drone engineering. Instead of starting from scratch, it asks, hey, how has nature already solved heavy lifting and extreme endurance? And the simulator doesn't just, visually mimic these animals. It translates their natural traits into hard, concrete mathematical modifiers. Take the albatross, for example. That bird spends days over the ocean without even flapping its wings. The simulator translates that exact behavior into a high-aspect wing and mission glide segments. It's a mathematical model of dynamic soaring that pulls energy right from wind shear, which can actually reduce cruise power by up to 22%. Or, consider the cheetah. It relies on fast-twitch muscles for immediate explosive sprinting. In engineering terms, this becomes burst power, signaling the use of supercapacitors. These are designed to provide massive temporary amp spikes during a heavy 220-pound takeoff, and that entirely prevents the primary lithium battery cells from overheating and destroying themselves early in the flight.
And this perfectly illustrates the crazy depth of the simulator's physics engine. Have you ever heard of the Weiss fog, clap, and fling mechanism? It's what bees use, this incredibly unsteady aerodynamic vortex generation to stay aloft when their little wings technically shouldn't generate enough lift. It's basically a localized manipulation of fluid dynamics. Now, when the simulator applies this very specific biological trick to a drone's actuator disk equation, it mathematically reduces the vehicle's hover power demand by up to 12.5%. Just think about that margin for a second. When you're desperately trying to lift 220 pounds on a tiny 55-pound frame, saving 12.5% on your sustained power draw is quite literally the difference between winning millions of dollars and crashing straight into the tarmac.
But the absolutely crucial point here is how all these different biological traits have to combine just to survive the actual DARPA course. The circuit requires 16 to 20 absolutely critical hover turns. That means you have to stop a swinging 220-pound payload dead in midair, rotate, and then accelerate all over again. If you've ever flown a drone with a suspended load, you already know that extreme pendulum dynamics and severe center of gravity shifts will violently rip an aircraft right out of the sky. So drawing from the Osprey, the simulator uses damped central sling loads to neutralize that crazy swinging momentum. Combine that with the cheetah's burst power for rapid acceleration out of the turn, and compliant, flexible spines to redistribute those dynamic kinetic loads, and suddenly, the drone bends instead of breaking. It manages all that aerodynamic chaos without just shaking itself apart.
All right, moving right along to the next phase, the synthetic Hunger Games, global mission analytics.
Let's see what happens when we take these theoretical biotraits and violently stress test them. The version 1.2 simulator generated 10,000 distinct bio-inspired drone designs and just dumped them into a grueling, simulated 5-nautical-mile competition circuit. You really have to treat this data like a high-stakes sporting event. And the reality here is pretty stark. The DARPA Lift challenge is incredibly unforgiving. Thankfully, there were absolutely no real test pilots involved in this phase because nearly half of all the designs, 47.2%, immediately failed and dropped out of the virtual sky. Another 27.3% managed to kind of drag themselves across the finish line, but they only took home a partial prize because they just couldn't hit that magic 4-to-1 payload ratio. In the end, only 25.5% of these highly advanced bio-inspired designs actually mastered the legendary ratio and claimed the full prize tier.
The anatomy of this simulated carnage is absolutely fascinating to look at. These virtual drones didn't just casually fail. It was brutal. The number one killer? The time limit. Over 1,400 designs simply couldn't battle through the simulated wind penalties fast enough without completely blowing their aerodynamic drag budget. Next up was power saturation. Even with those supercapacitors integrated, over 650 designs demanded way more sustained amps than their batteries could physically output. This intense current draw caused catastrophic voltage sag, which essentially drained the drones to death right in midair. And finally, hard touchdowns. Imagine this, almost 650 drones made it all the way to the end, only to smash right into the dirt. Why? Simply because they lacked the Tiger's robust landing gear trait, so they couldn't absorb the massive kinetic energy of a heavy, 220-pound descent.
Which brings us to the final piece of the puzzle, building the ultimate drone, insights for the future.
So, what does this all mean? What do we actually learn from all this virtual destruction? Well, the real value of the simulator isn't just watching virtual drones crash and burn. It's looking closely at the survivors. By analyzing the rank 10 designs, the perfect scores that achieve the 4-to-1 ratio under max turbulence, real-world engineers can reverse engineer that success. And when we look at those top survivors, a pretty surprising synthesis emerges. You might assume that mashing up a bat's folding wings with a bee's unsteady aerodynamics would result in some wildly complex, over-engineered machine, but the simulator explicitly points out a simpler thrust architecture likely reduces integration risk and improves build reliability. It turns out the absolute best drones borrowed brilliant structural tricks, like using cheetah-inspired tension cables instead of heavy, rigid frames to save critical empty mass, but they kept their actual thrust and motor layouts astonishingly simple and perfectly reliable.
The report distills all of this incredible data into a highly practical blueprint that you could actually apply to your own projects. Step 1, you've got to anchor yourself to the immovable physics, that strict 55-pound empty mass constraint. Literally everything flows from that single number. Step 2, choose your bioarchetype combination carefully. Ask yourself, do you need the dynamic soaring efficiency of an albatross or the violent off-the-line burst power of a golden eagle? Step 3 is selecting your frame material. You want to focus entirely on massive weight reduction through structural efficiency. Prioritize things like tendon-inspired tension cables over solid, rigid beams. And finally, Step 4, size your rotors for distributed thrust. You have to ensure you have enough absolute control authority to counter a sudden gust of wind while lugging around a swinging 220-pound block of dead weight. It really is a precise, step-by-step translation of millions of years of evolution directly into functional aerospace hardware.
The takeaway here is honestly pretty profound. When we hit a massive wall in conventional engineering, like when our lithium batteries are simply too heavy and our aerospace-grade carbon fiber is just too stiff, the solution might already exist. It's a brilliant illustration of how the intersection of evolutionary biology and extreme computational engineering makes solving impossible physics an actual reality. The answers to a $6.5 million aerospace challenge are quite literally flying around outside our windows. I want to leave you with a final thought to ponder today. If you were handed exactly 55 pounds of wire, carbon, and silicon, and someone told you that you had to lift 220 pounds straight up into the sky, What biological trait would you engineer into your own heavy-lift drone? Think about it. Thanks for joining me on this explainer, and remember to keep looking to nature for the next big leap.